Hi there. Thanks for stopping by. We've been through a lot. I think this is the last lesson that we're going to do this year. Just got some soup here. You know, a famous mathematician once said the following. When you're cooking a large pot of soup, you don't need to eat all of the soup to decide if it needs more seasoning. You just need to take a spoonful, provided you've given the soup a good stir. Now, what has that got to do with mathematics? That is good. Well, it has to do with sampling methods. Consider all of Saugeen Shores. There's a certain percentage of people from the Saugeen Shores area that are left-handed. That's a number. It's a number we don't know, but it does exist. Maybe it's 10%, maybe it's 15%, maybe it's 50%, though I highly doubt it. We have sampled a little over 100 people to try to guess what the left-handed rate is in Saugeen Shores. Now, have we given the soup a good stir in this case? Not really, because all the people we asked are from our households, so they don't really represent a good stirring of people from Saugeen Shores. But we're still going to use those numbers anyways. Today's all about hypothesis testing, and it's the final lesson in our data management class. So come on, let's go get started. So before we begin this lesson and dive into this first question, I'd like to point out that if you haven't looked over the binomial distribution and normal approximation stuff from the last lesson, you really need to understand that in order to understand this. So you might need to go back to that if you haven't already. Let's look at this first problem. Suppose we have some condition and we have a drug out there. We're just going to call it drug A, and it is known to be effective at treating the condition or curing it 80% of the time. Suppose a new drug is produced, and we're going to call it drug B. And drug B is tested on a random sample of 150 people, and it's found to be effective for 135 people, which is 90%. So in some ways, better than drug A. The question is, does that mean that drug B is more effective than drug A? Why might that answer not be clear? Well, one thing you might realize right away is 150 people isn't a lot of people. And you could say it's a poor sample for two reasons. One reason is maybe that's not enough people, and it could be a flawed study as well. Perhaps they didn't really have a good random sample of people. Okay, that refers to that idea of stirring the soup before you taste it. Perhaps they didn't get a good sample of people. Maybe those people had something in common. Maybe the condition they had wasn't as bad as most people who have the same condition. So although this is a possibility, a flawed study, let's say that it's not. Let's say that the study was done good and it was a good random sample of 150 people. That still doesn't necessarily mean that drug B is more effective, because drug B could have got lucky. Maybe it just by random chance happened to do better than drug A when it's not actually better. For example, if we go back to drug A, if you gave drug A to 150 people, you would expect that 80% of 150 people, or 0.8 times 150, you'd expect 120 people to be cured from drug A, not 135. But that doesn't mean that you necessarily cure exactly 120 people. It's kind of like the multiple choice test. Although you expect to get a fifth of the questions correct when you guess on a multiple choice test, that doesn't mean that that's exactly what's going to happen. In fact, chances are you'll get more or less questions correct just by chance. So the same thing applies here. You probably won't have 120 people cured. It'll probably be a little bit more or a little bit less. Is it reasonable that it might be as high as 135? So in a way, what we're doing is we're assuming that drug B is exactly the same as drug A. And what are the chances that drug B, just got lucky? One thing you might look at, one calculation we can do for drug A, what are the chances that drug A cures exactly 135 people? Or actually, let's start with that. The chances that drug A cures exactly 135 people would be 150, choose 135, times 0.8 to the power of 135 times 0.2 to the power of 15. That calculation that we've seen quite a lot of. So that answer, if you do that, by the way, these numbers are too big probably to type into a regular calculator. You need a computer calculator. You'll get a very low number. In fact, it works out to a way less than 1%. So it's very unlikely that drug A would cure 90% of 150 people. But you could also look at what is the probability that drug A cures exactly what you would expect, 120 people. That probability should be a lot higher, and it is. It works out to about 8%. So this is, we're kind of answering the question right now. We're looking and say, look, drug A, it's not too likely it would cure exactly 135 people. But it's also not too likely that it would cure exactly 120 people. I mean, 8% is within the realm of possible, but it's likely that it's some range of values. So we're kind of starting to answer this question a bit. I'm gonna look at this whole question again, and I'm gonna go through what's called hypothesis testing. We're gonna take drug B, and we're going to assume that it's just as good as drug A, and then we're going to look at the probability that we got these results in this experiment right here and decide whether the experiment was a fluke or whether it actually shows something. If you ever read articles about statistics, you sometimes hear the phrase statistically significant or statistically insignificant. So we might talk about drug B and we say, are the results of the test for drug B, so that was 135 out of 150 people being cured, is that statistically significant for us to make the conclusion that drug B is in fact a better drug? Here are the steps we follow. This is called hypothesis testing. Okay. So I'll give you the steps, and as I'm doing the steps, we'll solve the problem with drug A and drug B. So we start with what's called a null hypothesis. And the word null refers to like no change or nothing interesting. And the null hypothesis, the notation we use is H. See that subscript 0? That's actually pronounced H naught. So in this example, H naught is our null hypothesis. And that for our test would be that drug B is just as effective as drug A. So we would say actually that our null hypothesis is the probability of we'll say success of drug A or drug B, pardon me, is 80% or 0.8. So we're assuming here that drug B is just as effective as drug A. Okay, and I'm going to call that a success. And notice that that is like our p-value, 0.8, our probability of success, and then 1 minus p is 0.2. So using a drug, either it's successful or it's not successful. That's an example of a Bernoulli trial, an example of a binomial distribution where we're concerned with how many successes are there. Okay, so that's our null hypothesis. We then state an alternative hypothesis that you want to prove or disprove. And this hypothesis should be simple and involves a slight change from the null hypothesis. So it's basically that the null hypothesis isn't true. So here, H1 would be that the probability of success of drug B is greater than 0.8. Not that it's equal to 0.9. We're going to find that we're not able to exactly determine that, okay? But we want to first test it against the null hypothesis. So it's a simple change that it's greater than 0.8. This part, step 3, this is a little confusing, but when we do the end of the question, you'll probably start to see what it means. We talk about what's a significance level. How strong must the evidence be to reject the null hypothesis in favor of H1? How much evidence do we need to do to make this our new conclusion, that drug B is better? Your significance level determines how often you're incorrect in rejecting a null hypothesis. In medical studies, they want significance levels that are quite high. So common ones are 0.05, which corresponds to I might be wrong 5% of the time, 0.01, which corresponds to 1%, and then 0.001 or 0.1%. There's no real simple answer for this. Right now, let's say we'll go with 0.01. That's often called alpha, by the way, in statistics, an alpha value of 0.01. And at the end, we can choose to change that, or we'll get a new significance level. basically what this means is I'm okay with concluding that H1 is true as long as I'm 99% certain that it wasn't from chance. We'll come back to that in a minute if that doesn't make sense yet. Okay, here's step 4, and this is where the math is done. Assume that the null hypothesis is true and calculate the probability of your data or results given the null hypothesis is true. And we actually kind of did this right here. We assumed that drug B was the same as drug A, and we found out what's the probability drug A cures exactly 135 people. So we sort of did that here. But actually, we're more interested in the probability that drug A cures 135 or more people, because we don't care if it's exactly 135. It could be 136, 137, and so on. So I know this is this is difficult to understand. We're kind of saying, let's assume that drug B is 80% effective. What is the probability that we got this result in our study just by chance? So think about what we're doing here. And I'm going to put a picture up here on the screen. There it is. That's our normal curve. If we assume the null hypothesis is true, that is that we assume that drug B is just as effective as drug A at 80%, we would expect 120 out of 150 people to be cured by the drug. What is the probability that we get 135 or more in our test? Because obviously that is a possibility. Okay, it might be a small possibility, it might be a big possibility. We'll look at that probability of this happening by chance and compare it to our significance level. All right, so we have a binomial distribution here. We have NP, N is 150. Our probability is 0.8, so NP is 0.8 times 150, which we've already calculated to be 120. That's like our mean value. Okay, if drug B is successful 80% of the time, then when you grab 150 people and treat them with the drug, you expect 120 of them to be cured on average. The standard deviation of that number is this calculation that we talked about in the last lesson, NP times 1 minus P, and take the square root of that, of course. So our standard deviation is that 120 times 1 minus P would be 0.2. And if you figure that out, you get about 4.90. So just to recap, if the null hypothesis is true, that is that drug B is just as good as drug A at 80%, and you were to give the drug to 150 people, you'd expect 120 of them to be cured, on average, with a standard deviation of 4.9. So we have a normal approximation of 120, 4.9 squared. What's the probability that you end up getting results that are greater than or equal to 135? That's the next question we're going to answer. Well, the first thing we should realize is that really when we do our z-score here, 134.5 and up will round to 135. And I know that that is a little bit confusing. It's a little annoying. If you used 135, you probably still get a pretty good answer, but technically anything at 134.5 would round up and would count as 135 people. Subtract from 120 and divide by 4.9. Remember here, we are calculating a z-score. So how many standard deviations, sorry about this mess here, how many standard deviations is 135 from 120? And if you figure that out, you get a z-score of 2.96. So 2.96 standard deviations above the mean. We then can use our z-score table, and unfortunately z-score tables is always less than or equal to. So what's the probability of getting a z-score less than or equal to 2.96? I hope you realize that's going to be a pretty high possibility. Let's just take a look at our z-score table. Okay, 2.96 is all the way down 0, 1, 2, 3, 4, 5, 6. 0.9985 is what we get there. So that answer is 0.9985. 0.9985. But that's the probability you're less than, and we want to know greater than. So the probability that x is going to be greater than or equal to 135 will be 1 minus 0.9985, or 0.0015. What does that mean? Well, that means that if drug B really has a success rate of 0.8, that the probability that you would have 135 or more people is only 0.0015. Or you could look at that as 0.15% if you multiply by 100. That is much, much lower than our significant level of 1%. So the chances of this happening by chance are so low that we can throw out the null hypothesis and replace it with H1. So we can conclude that drug B is more effective than drug A. We decided that we were okay with a significance level, or I decided that the significant level was going to be 0.01 or 1%, meaning we were going to be okay if this conclusion was wrong 1% of the time just by chance. As it turns out, we can be satisfied that this conclusion is true way more than 1%. We have a pretty good significance level here, 0.0015. Okay, so if we had chosen this as our significance level, pardon me, we would actually not be able to make this conclusion, because there is that very, very small chance that this conclusion is only true because of randomness. So it's unlikely that this conclusion is not true. We can be fairly certain that it's true, okay, because it is a lower number than our significance level. Okay, let's try a couple more examples. So let's look at polling and a presidential election. Now, I want you to notice that these are made-up numbers. I just throw them out there, okay? This isn't, I don't know what the polls are like. Okay, so, but I know one thing's for certain, almost certain, that in the fall of 2020, the U.S. will vote in a new president, and that will almost certainly be between Joe Biden and Donald Trump. So let's suppose that polls, which are just large surveys across the United States, estimate that Donald Trump is the choice of 47% of voters and Joe Biden has the support of 53% of voters. Now, this is unrealistic because those numbers would probably never add to 100 because there'd be people who are undecided voters. But we want to keep things simple, so we're just going to assume that that is true. Okay, so suppose a newspaper, often newspapers do polls, surveys 1,500 people, and finds that out of those 1,500 people, 56 support Joe Biden, which is 840 people, and 660, or 44%, support Donald Trump. So we had more support for Joe Biden than you would expect, is one way of looking at it. Is that result significant, or is it not really that surprising that we would have got that? Could we make the conclusion that Joe Biden's support is going up and Donald Trump's support is going down? And we're going to use that 5-step approach of hypothesis testing. And I've started the solution here for you. Let's look at it together. Let's the null hypothesis be that Trump has 47% of support from voters. That no, the survey did not change anything at all. We start with that hypothesis and we try to prove or disprove it. Another way of writing this hypothesis is we could say that P equals, now we can choose to decide that either Trump support is a success or Biden support is a success. I don't really like to think of Trump support as a success personally, but we'll say that we'll use that as our p-value. So we're saying that the null hypothesis is that Trump still has 47% of support, or p equals 0.47. Our alternative hypothesis is that Trump has less than 47%, so that the probability of someone supporting Trump is less than 47%, or less than 0.47. And why are we doing that? Well, because we're testing this newspaper's new survey, which gives his support down to 44%. Okay, next is to choose a significance level. And I understand you don't need to necessarily statisticians say you should do this before you start looking at your results, that you should decide what your significance level needs to be. You shouldn't let the results decide for you. Let's use 0.05, not nearly as high. So we're basically going to do the math, and we'll accept the fact that our conclusion could be wrong 5% of the time, so that we're 90, if we do replace the null hypothesis with this alternative hypothesis, that will be sort of 95% certain that we were correct, that it wasn't due to just chance. And then we move into step 4, where we actually do the math and the calculations, where we assume that H naught is true. We assume the probability of someone voting for Donald Trump is still 47%. We can again think of this picture, and we can imagine a binomial distribution. Okay, so we would expect that if Donald Trump has 47% of support, we can look at NP, which is the expected number of people that would choose Donald Trump in the survey. That's 1,500 times 0.47, which works out to 705. So when you survey 1,500 people, if Donald Trump has 47% of the support, you'd expect 705 people would choose him. We didn't get that, though. In this survey, they got 660, so below that. What's the probability that if he really has 47% of the support, that he would have 660 or less people choose him in that survey? Could that happen by chance? So, of course, we have the 705 as our mean here. So that's the mean, like if you imagine repeatedly grabbing 1,500 people, asking them who they're going to vote for. If Donald Trump has 47% of the support, you'd expect that on average 705 people would say Donald Trump. However, by chance, it will often or almost always be more or less than 1,500. What's the probability it ends up being 660 or less? And then we'll compare that. So the standard deviation, again, we need this calculation. So NP, 705, and then 1 minus P would be 1 take away 0.47, which is 0.53, which gives us a standard deviation of approximately 19.33. And so this curve I've drawn here is normally distributed with a mean of 705 and a standard deviation of 19.33. That describes what we would expect to happen with 1,500 people in this survey if the null hypothesis is in fact true. So now again, we're looking at what's the probability that we come up with 660 or less. Why do we want to know less? Because we want it, we want to compare it to H1, which is the fact that his support has dropped. Okay, and I mean the probability at 660 or larger, that's going to be a really big number. Okay, that's not going to be shocking. Where 660 or less might be small. Okay, so we calculate a z-score. Again, since our data is discrete, we actually need to use 660.5. And the reason we need to know that is that technically 660.1, 660.2, that would all round to 660. Now I know that you might be thinking, 660.5 rounds up to 661, and you're right, but we want 660.499999. Well, we can just round that to 0.5, so that's how we do that. Even if you use 660 instead of 660.5, you probably get close to the correct answer. Our z-score here is about negative 2.30. So this is 2.3 standard deviations from the mean. Hopefully you realize that is going to be a small number when we look it up in the table. Let's just take a look at that number. Okay, it's here in OneNote, negative 2.30. So negative 2.30, there it is right there, 0.017. And then our last step is to compare that to our significance level. I said we should use a significance level alpha of 0.05. This significance level is below that. So we toss out the null hypothesis and we make the conclusion. Therefore, Trump's support is less than 47%. Why? Well, because if his support was only 47%, then the probability of getting only 660 people out of 1,500 choosing him in this survey is a little over 1%, that would happen by chance. So we can be confident this is our significance level. We were okay with the fact that there's a 5% chance we were wrong, with a 95% chance that our conclusion is correct. Notice if we had set our significance level at 0.01, we would have just missed it. And any statistical study would publish this value as well. Okay, this important number here that tells you how sure you are of your results. Now, obviously, there are other reasons we're assuming here that this survey was done correctly, that it was a good random sample, that there's no sampling bias, because this math does not take into account any sampling bias. We'll do one more example. Okay, let's use our roulette wheel again for this last example. So roulette wheel at a casino. And of course, when you spin the roulette wheel, they drop a ball and it lands on one of these slots, and you might gamble on where it's going to land or whether it's going to be red or black or a specific number. Now, what they often have at casinos, so I've been told, is a little screen that looks like this, where they show the last results of the spins. Now, this one's probably been posted on the internet because of the bizarreness of all the 19s and 20s there. But in any case, it shows you what the last spins are like. And I think the idea is to get people who are betting to think they've figured out some kind of pattern, so they're more likely to play. I don't know. But in any case, let's look at this. Suppose it shows 30 results. So the last 30 spins were all red. Sorry, 20 of the last 30 results were all red. So someone looking at that screen sees a lot of red. And the gambler makes a hypothesis that maybe the wheel is rigged and it's spinning more reds than it is blacks, in which case maybe he should be betting or she should be betting on reds. Are they correct? Well, let's take a look. So step one is, if we're going to do this mathematically correct, then we should state a null hypothesis. So we need to think a little bit about this, maybe even before we get into our null hypothesis, and realize that in reality there are 38 numbers. The probability of getting red is 18 out of 38 if you count the red squares, or exactly 9 out of 19, which rounded is about 0.4737. That means that the probability it's not red, which we'll call a not success, would be 10 out of 19. Okay, because there's 20 numbers that aren't red. Or 1 minus 0.4737, which is about 0.5263. So our null hypothesis might be that no, it is not rigged. So our null hypothesis in this case is the probability of getting a red is still only 0.4737, or 9 out of 19. That hasn't changed. The alternative hypothesis is the fact that the wheel is rigged and that the probability of rolling a red is higher than 9 over 19 or higher than 0.4737. What should our significance level be? That's the third step. If you look back at the steps I outlined, you don't need to follow the steps exactly. They're just a guideline. How certain should we be? I'm going to say in this case, our significance level should actually be pretty high. Let's look at 0.01, but really you might argue it should be 0.001. And the reason for that I'll talk about in a little bit, okay? We'll talk about why the significance level in this example should be probably pretty high. Okay, now we get into the math. This is where we assume the null hypothesis is true. And we can start thinking about this picture here again. Okay? If you spun the wheel 30 times, you would expect how many red numbers? Well, 30 times 9 over 19, or 30 times 0.4737, is equal to 14.2105. Or 14.21 is going to be good enough here. So you would expect that in 30, for n equals 30, you would expect 14.21 reds. You would not expect 20 reds. So we're going to say, okay, assume that this is the probability of getting a red. What's the probability that you ended up with 20 reds or 20 or more? What's the probability that that happened, assuming the null hypothesis? So again, we look at the standard deviation, the square root of np times 1 minus p, or 14.21 times 1 minus p, which would be our point, either 0.5263, or you could use 10 over 19. And when you do that, you get a standard deviation of about 2.735. So we can say that our curve here is normally distributed 14.21 and a standard deviation of 2.735. And then we use the squared in the notation there. And so we start looking at z-scores next. So we want to know, what is the probability that you get 20 or more reds, given the null hypothesis is true? Now again, anything that's 19.5 or up will round to 20. So we'll use 19.5, subtract 14.21, all divided by our standard deviation. So we're calculating a z-score is just the number of standard deviations from the mean you are. So a z-score in this case is 1.93. Now again, we can only use our tables for less than. So what's the probability that you have a z-score less than 1.93? So I go to my z-score table. Is let's see, 1.9, there it is, 0, 1, 2, 3, 0.9732. That's from the table. But we want to know the probability that it's less than that. So the probability of, or sorry, greater than that. Okay, this gives us the probability that we're under 20. So this part of the curve here, we want to know everything but that. So we subtract from 1. And we get 0.0268. So the probability that you get 20 or more reds on the wheel is only 2.68%. That, in this case, according to our significance level I chose, which was right here, means we keep the null hypothesis. We say that this is not significant enough. And so we say, therefore, the wheel is not rigged. Or there's not enough evidence to say that the wheel is rigged. Okay, we would say that, look, yeah, there's a 2.68% chance that you would have 20 reds out of 30. That's not that bizarre. That's definitely possible. Now, if I'd chosen a significance level of 5%, I could say the wheel is rigged. Well, I think you should, I chose this as my significance level because I think you should need pretty strong evidence that a wheel is rigged. And the reason is this wheel is being spun all the time, all day long. All sorts of strange things are going to happen. And so we should see something really, really bizarre to convince ourselves that the wheel is in fact rigged. Because to be honest, this means, what this result means is, look, if you continually spun a wheel 30 times, you would find that out of those sets of 30, that almost 3% of the time you would have 20 or more red numbers. Well, that wheel is spun, I don't know how many times in a day. So you're going to see this happen. So I think that's why the significance level should be pretty high here. And we would say, according to our significance level, the wheel's not rigged. We keep H naught, we keep the null hypothesis, and say the probability is in fact equal to 9 out of 19 that you get a red, that it's not more likely to give a red. There's not enough evidence. This is not statistically significant, this 20 out of 30. Okay, I hope you're not too frustrated. This is a difficult lesson. It really brings together everything we've done all year. it's also the last lesson. So I really want to thank you guys for sticking with it online and doing the best that you can. It hasn't been ideal, but this is the way I've been had to teach. I hope that if you are frustrated with this, you will give me an email and let me know. I will walk you through anything that you need help with. I'm going to give you a couple examples to work on now with full solutions, so I recommend trying those before moving on to your year-end assignment. And please don't give up on that assignment at the end of the year. I'm really, really willing to walk you through it if you're having difficulty. Then I'd rather help you than have you give up on that assignment. So reach out anytime, and thanks again, and bye for now.